This is a story of O, B, and A-type stars. They're the most massive types of stars on the H&R diagram. They live their lives quickly and they die quickly in a violent death. At the end of their lives, they become red supergiants, and these red supergiants make up all the elements in nature down to the element iron, and then the red supergiant is going to collapse and go supernova. What used to be the upper layers of the star are now expanding outward at a fraction of the speed of light, and almost all the elements on the periodic table beyond iron, heavier than iron, are made at this point. I call these stars Bob the Builders, the O, B, and A stars. They make all the elements in the universe. Everybody, me, you, your dog, we've all been inside of these gigantic O, B, or A stars in the past. As the father or mother of the sun, we're probably third generation star. The son had a father, the father had a mother, and so on. They've been making all the elements heavier than iron. After all the elements are built during the supernova explosion, next the core of the star is going to collapse. If the core has more than 3 times the mass of the sun, the core will become a black hole. If the core has less than 3 times the mass of the sun, the core will collapse and become what is called a neutron star. A star about the size of San Diego, approximately 10-15 miles across. If the star has more than 3 times the mass of the sun, then the star will become a black hole. This incredible object that tears the space and time. So this is that story, the story of the evolution of the massive stars after they get out of the main sequence. We start with the core of a massive star when the hydrogen has run out. Since there is no more hydrogen, the star will collapse, and once it collapses, the temperatures will go up. This is the beginning of the evolution of a massive star. Every time the upper layers collapse, the temperatures rise, and every time the temperatures rise, the star is able to burn heavier and heavier elements. This collapse results in a higher temperature around the core. The hydrogen that is virgin and untouched outside the core is now ignited in a shell. This shell will make way too much energy, and the star will now expand to become a red supergiant. Once the hydrogen in the shell is depleted, the star collapses, temperatures rise again. This time temperatures rise to 100 million degrees Kelvin. The helium core at this point ignites. This is called a helium flash. The star expands again. Next, helium in the core is depleted. Star collapses again. Temperatures rise again. And a shell of helium is going to start burning outside of the core as well now. Once the helium in the shell ignites, the star expands again and is a red supergiant. Next, the helium in the shell is depleted. The star is going to collapse again, temperatures will rise. This time temperatures rise to 1 billion degrees and the core is now carbon. Carbon burns at 1 billion degrees. Now the carbon core will ignite and the star will expand again. So now let's review and see what's happened so far. The blue star is living on the main sequence for a long time. But a time comes when the hydrogen is depleted in the core and the star collapses. Temperatures rise and the hydrogen in the shell ignites and the star expands to become a red supergiant. The hydrogen is depleted again and the star collapses. This time temperatures rise again and helium is ignited in the core. The star becomes bright again and big. So this will go on until we reach iron. One core after another is going to ignite. Let's see the details real fast. Once the carbon in the core is depleted, the star collapses again. And this time, carbon has left behind neon. Neon at this point is also going to start burning. So we have a neon core with a carbon shell, helium shell, and hydrogen shell, all burning at the same time. And the same thing is going to happen to neon, and the elements are heavier than neon. So next we're going to have an oxygen core, neon shell, carbon shell, helium shell, hydrogen shell. Next is magnesium's turn to burn in the core. After magnesium, we're going to have a silicon core now. Silicon perhaps burns in one day. Once the silicon burns, we're going to have an iron core. Now we have reached the end. We have an iron core. It takes more energy to fuse iron than the energy the star can get from the fusion of iron. So iron is useless. Now the star is going to collapse because the core is going to start collapsing. As the core collapses, the star crashes towards the core and ricochets off the core and goes supernova. This is a supernova remnant called the Crab Nebula. It was observed in the year 1054 by Native Americans and the Chinese astronomers. No records in the European literature. The colors in the Crab Nebula are representative of the elements that existed inside the star. As an example, the green is oxygen, the yellow is sulfur, the red hydrogen, and so on. The blue is perhaps nitrogen. And the Crab Nebula has been expanding for a long time now, and in a man's lifetime we can observe changes. During the supernova, we can make all the elements heavier than iron. Some of the elements are very difficult to make, and because of that, there is new research that shows a gigantic bubble of neutrinos goes off after the supernova explosion, and these bubbles help stabilize some of the elements so that can actually exist in nature. So your gold, your aluminum, your platinum, your silver, a whole bunch of elements are made at the supernova event. Now this is the core that we're going to have left. The core is an iron core. Now if the collapsing core has more than 3 times the mass of the sun, the collapse yields a black hole. So this entire core is going to collapse, and if the core has more than 3 times the mass of the sun, it's going to go either a black hole, or if it has less than 3 times the mass of the sun, it's going to end up as a neutron star. In a neutron star, the star becomes so small that there is no room for the electrons and protons to exist. So they have to exist simultaneously together, and they become neutrons. And this is why we call the star a neutron star. So the star is going to be a gigantic ball of neutrons, about 10 to 15 miles across. A teaspoon of this material weighs approximately 1 billion tons. Amazing. It's one of the most extreme densities in nature, just above the black holes. A neutron star's size is very, very small. It's incredibly small. And so you can see the neutron star in comparison to the city of San Diego. There's a principle called Pauli exclusion principle in quantum physics. It says that no 2 electrons or protons or neutrons can occupy the same quantum state at the same time. That means 2 neutrons can occupy the same space and the same time. And so the neutrons refuse to be compressed anymore. If the star has more than 3 times the mass of the Sun, this neutron pressure will also be overcome. So that's the reason that the star does not collapse anymore, is because of the Pauli exclusion principle, what we call neutron pressure. This neutron star has an axis of rotation and also an axis that we call the magnetic field. So this is the south and this is the north pole of the magnetic field. And neutron stars rotate extremely fast, at the beginning perhaps hundreds of times per second, and eventually slowing down. The neutron star in Crab's Nebula rotates approximately 30 times every second. The magnetic poles is where the electrons get caught and they spiral and they emit a synchrotron radiation. We can see the synchrotron radiation if you're at the right place. If you happen to be at the end of the north or south magnetic poles, every time the star rotates, you'll be able to see it. This kind of a star is called a pulsar, if you can see it from the Earth. If not, we just see a neutron star. So neutron stars are not pulsars necessarily. Now let's see how this lighthouse works. If you happen to be in the direction of north or south magnetic poles, you can see this beam of radiation like this. So you happen to be in the right place to see this as the beam sweeps you by. This is a pulsar. Now, if the star has more than 3 times the mass of the Sun, it will continue to collapse. Neutron pressure is not going to stop it, and the star is going to collapse to a singularity, where the density becomes infinite. At this point, the star will tear up the space and time, and all we can see of the star is now mass, rotation, and charge. Nothing else is left of the star in this universe as far as we can see. This is called singularity. This is a point that contains the mass, rotation, and charge of the black hole. Now, this is the final resting place of the star. You don't really know where it is. It doesn't seem to be in this universe, but it shows mass, rotation, and charge. Surrounding the singularity, there's a volume of space that has been curved infinitely. The limit of this curved space is called the event horizon. So inside of the event horizon, space and time are curved infinitely. However, outside, it is not curved infinitely, and as you get closer and closer, gravity tends to pull you apart